Alright, in this video we're going to do some examples involving the net change and the average rate of change of a function. So here we're given the function f of x equals x minus 3 squared, and we're asked to find the net change and the average rate of change. And I abbreviate average rate of change. It's just too many words for me to write out. I'm kind of lazy like that. So just average ROC, that means average rate of change, between the points x equals 1 and x equals 3, and the points x equals 4 and x equals 7. Alright, so I need to get the net change and the average rate of change between two different sets of points. Alright, so for the first part, for x equals 1 and x equals 3, remember the net change of the function is the difference in the output values. Right? So if I think of the x equals 1 is my x1 value and the x equals 3 is my x2 value, well then I need to do basically y2 minus y1. So I had to figure out, well, what's the y value when x equals 3? What's the y value when x equals 1? Alright, and I drew the picture of the graph up here just so after we figure this out, I'll just kind of show you graphically what this means and what all these numbers represent. So I need to find x, basically f of 1 and f of 3. Right, to get my y coordinates, and then I can use those to get my net change and my average rate of change. A lot of times for the net change problems and for the average rate of change problems, a lot of times they only give you the x values. So the first thing you have to do is figure out what the y values are that go with those x values, right? Which is by plugging the x value into the function. Right, so f of 1 is equal to parentheses 1 minus 3 squared, which is negative 2 squared, which equals positive 4. Right, and then f of 3. If I plug x equals 3 into my function, it's going to be 3 minus 3 squared. Well, 3 minus 3 is 0, and 0 squared equals 0. Right? So the 4 is like my y1 value, and the 0 is like my y2 value. Right? Those are the output values that correspond to my inputs of x equals 1 and x equals 3. Alright, so I've got those output values now. To find the net change, and I really did not leave myself enough room to do this. I'll have to write it on the side here and then probably erase it later. Right, so the net change for this first one, remember, net change is just the difference in the output values, the difference in the y values. Just be careful, right? For net change, it always has to be the y2 minus the y1, or the f of b minus the f of a, the one on the right minus the one on the left, right? And since 3 was my bigger number, 1 was my smaller number of my x values, it has to be f of 3, which was 0, minus f of 1, which was 4, and so my net change, 0 minus 4, equals negative 4. Right, so the net change of this function, x minus 3 squared, between x equals 1 and x equals 3 is negative 4. Right, what does that mean, graphically speaking? Well, for my point here at x equals 1, which has a y coordinate of 4, to my point here at x equals 3, which has a y coordinate of 0, the function drops 4 units. Right, it goes from 4 down to 0. It has a net change of negative 4. Right, the net change is just the difference in the y values. It's the difference in height between those two different points of the function. Right, and if the first point is higher than the second point, then your net change is a negative value because the function is decreasing, it's going down. All right, so that's my net change. Now if I want to find my average rate of change between those 2 points, if you recall, and if you haven't watched the video I did, I just made one on net change and average rate of change where I explain what the formulas are and kind of how they work. So if you haven't seen that yet, you might want to check that out before you watch any more of this one. But if you recall, if you have watched that video, the average rate of change is, there's 2 formulas we can use. The one that we're always given is f of b minus f of a over b minus a. But all that really is y2 minus y1 over x2 minus x1. Right? The average rate of change is the slope of the line that connects the 2 points that we're talking about. In this case, it's the line that connects those 2 points on the graph at x equals 1 and x equals 3. Right? So the slope of that line that I just drew up there, that's going to be the average rate of change of this function from x equals 1 to x equals 3. Right? So my y2 value is 0, minus my y1 value, which is 4. And notice that numerator of average rate of change, that's exactly what I did to find the net change. Right? So another way to think about the average rate of change, the average rate of change is the net change divided by the difference in the x values, which is 3 minus 1. Right? And when you're doing net change and average rate of change, remember you always have to do the second point minus the first point. Right? The one on the right minus the one on the left. So we get negative 4 over 2, which is going to equal negative 2. Right? So the average rate of change of this function between x equals 1 and x equals 3 is negative 2. Right? So net change and average rate of change, they're related, but they tell you 2 different things. Right? The net change just tells you how much does the function value change from x equals 1 to x equals 3. Well, it goes down 4 units, so my net change is -4. The average rate of change is, well, that's my net change, but since I moved over 2 units, how much does it go down on average between x equals 1 and x equals 3? So basically the -2 is saying each time you move over 1 unit, you're going down 2. Over 1, down 2. That's the slope of -2. Right? So that's the difference between the net change and the average rate of change and what they mean. Right? So that dotted line that I drew up there connecting those 2 points, that line has a slope of -2. That's our average rate of change of the function. Right? Notice the function itself is not a straight line. Right? So it's not like you're going down 2. Every time you move over 1, you're actually moving down 2. Because we can see when x equals 2, that dotted line does not match up with the curve. But on average, between x equals 1 and x equals 3, when you move down 1, when you move over 1, you move down 2. All right, so that's the net change and average rate of change for those two. And I'm going to erase this so I have room to do the second one that's up here. All right, so same function. Now we want to find the same 2 things from x equals 4 to x equals 7. All right, so same thing. They give us the x values, but not the y values. So first thing I have to do is plug the x values back into the function to get the corresponding y values. Right, again, the lower number we have is our x1. The bigger number we have, the 7, is our x2. All right, so I want to find f of 4, which is going to be 4 minus 3 squared, which is 1 squared, which equals 1. That's going to be my y1 value. And then I want to find f of 7. Right, so f of 7 is going to be 7 minus 3 squared, which is 4 squared, which is going to equal 16. That's going to be my y2 value in this case. All right, so remember, net change and average rate of change, for most functions, they're not the same when you choose different x values. Right, we saw up here, right, the net change was -4 and the average rate of change was -2, I think it was. I should remember, there's only like a minute ago. So I think those were the answers we got for that one. For this one, though, we're going to get different numbers for the net change and the average rate of change because we're using different x coordinates. You can see from the graph, from x equals 4 to x equals 7, the graph is changing in a different way than it changed between x equals 1 and x equals 3. So we're going to get different results for the net change and the average rate of change. All right, so net change. Remember, net change is just the difference in the output values. Graphically speaking, it's the difference between the y coordinates of those 2 points on the graph. Well, my y2 is 16, my y1 is 1, so it's y2 minus y1, which is 16 minus 1, which equals 15. Right, so the net change of this function between x equals 4 and x equals 7 is 15. Right, meaning from this point where x equals 4 to this point where x equals 7, the graph increases 15 units. All right, that's what net change is telling us, just what's the level at x equals 4, what's the level at x equals 7, what's the difference? And since the graph is increasing between those 2 points, the net change is positive, right? Whereas between 1 and 3, the graph was going downward, it was decreasing, so the net change was negative. Also, the average rate of change was negative. Here, the average rate of change is going to be positive because, again, the graph is increasing between these 2 points. Right, so to calculate my average rate of change, that's the slope formula, y2 minus y1 over x2 minus x1, right, which the y2 minus y1, that was that 15 that we had up here, right? Remember, the net change is that numerator for your average rate of change formula. And then the x2 minus x1 is 7 minus 4, which that equals 3, and then 15 divided by 3 is going to give us 5. Right, so between x equals 4 and x equals 7, this function has an average rate of change of 5. Which again means on the graph, if I draw the line between those 2 points on the graph, this line, this dotted line that I just drew here, is going to have a slope of 5. All right, so that's the average rate of change and net change of a function. Couple examples of doing that. I'm going to pause the recording here and then put up some more examples that we'll do that are kind of similar to this, but a little bit different. All right, got a couple more examples up here. This one, we have actually a function defined numerically as a table. And if you haven't seen the video I did where I talked about the 4 different ways you can represent a function, mostly we see, algebraically, which is, with equations and formulas and stuff. But you can also represent a function numerically with just a table of values. And this particular function is about the temperature in degrees Fahrenheit at certain times during one afternoon. Right? So the times go from 12 until 5. The temperatures are over there, and we want to find the average rate of change between 1 and 3. All right, so between 1 o'clock in the afternoon and 3 o'clock in the afternoon, what was the average rate of change of temperature? Well, at 1 o'clock, the temperature we can see was 62 degrees. All right, so one is like my x1, 3 o'clock would be like my x2, my y1 would be 62, and my y2, right, at 3 o'clock the temperature was 67 degrees. So my y2 is 67. All right, so in this case, we don't have to plug the numbers into the equation to figure it out. We just have the output values in the formula, so we got them. Right, so the net change in temperature from 1 to 3 would be 5 degrees Fahrenheit. Right, between 1 o'clock and 3 o'clock, the temperature went up 5 degrees Fahrenheit from 62 to 67, so it's a positive 5 would be our net change. But for average rate of change, it would be y2 minus y1 over x2 minus x1. All right, remember, average rate of change is just the slope formula. So 67 minus 62 over 3 minus 1, which is 5 divided by 2, which would be 2.5 degrees Fahrenheit per hour. Right, when we're doing average rate of change and it's a word problem, you know, an application to real life things, the average rate of change is not just 2.5. There's some units attached to it, right? How does that relate to real life? Well, it's 2.5 degrees Fahrenheit per hour. Right, that doesn't mean that every hour between 1 and 3 that the temperature went up 2.5. We can see between 1 and 2 it went up 4 degrees, and then between 2 and 3 it only went up 1 degree. Right, but on average between 1 and 3 it went up 2.5 degrees Fahrenheit per hour. That's average rate of change. Right, between 2 and 5 o'clock, same deal. Right, at 2 o'clock the temperature was 66. At 5 o'clock it was 58. So my net change from 2 to 5 would be a negative 8 degrees. Right, from 66 degrees down to 58. Now, over those 3 hours, the temperature dropped by 8 degrees Fahrenheit. All right, and then to find my average rate of change, well, it's going to be 58 minus 66 over 5 minus 2. Right, y2 minus y1 over x2 minus x1, which is negative 8 over 3, which would be negative 2.6 repeated degrees Fahrenheit per hour. Right, I think that's what that comes out to. 3 goes into 8. Yeah, 2 times with 2 left over. Yeah, so it's negative 2.6 repeated. All right, so so between 2 and 5 o'clock, on average, the temperature dropped 2.6 degrees Fahrenheit per hour. Right, we can see that's not what happened. Right, between 2 and 3, it actually went up 1 degree. Then it dropped 3 in the next hour, and then it dropped 6 in the next hour. But on average, over those 3 hours, the temperature went down 2.6 repeated degrees Fahrenheit each hour. All right, so that's average rate of change. Given a table of values, it's actually easier to do because the y values are already there. You just have to pick the right ones out and put them into the formula. And again, the average rate of change formula is just calculating slope. All right, the next example here real quick. F of x equals 3x minus 5. We want to find the average rate of change between x equals 0 and x equals 1, and then x equals a and x equals a plus h. All right, so for x equals 0 and x equals 1, I need to find f of 0 and f of 1. F of 0 equals negative 5, right? That would be 3 times 0, which is 0, minus 5. So I get negative 5. F of 1 would be 3 times 1, which is 3, minus 5, which is negative 2. All right, so my average rate of change, again, is y2 minus y1 over x2 minus x1. Right? These are my y values, so it's negative 2 minus negative 5 over 1 minus 0. So I get, let's see, negative 2 plus 5, so 3 over 1, which equals 3. All right? And for this one, I'm actually going to change this one because we're not going to have enough time to go through that. That a and that a plus h, that's something that we call a difference quotient, which I'm going to do another video after this on the difference quotient. So if you're interested in that, check it out. But just to do another quick one here, let's say we do x equals 1 and x equals 3, just to do it real quick. Right, so f of 1 is going to be negative 2. F of 3 times 3 is 9, 9 minus 5 is 4. And then if I do my y2 minus y1 over x2 minus x1 is 4 minus negative 2 over 3 minus 1, which is 6 over 2, which guess what? Also equals 3. All right, so here's the deal with this type of function, right? This is what we call a linear function, right? Because it has an x to the first power. It's in that form, f of x equals mx plus b. If you have a linear function, the rate of change is constant. Right? No matter what numbers I choose for my x1 and my x2 or my a and b, when I calculate the average rate of change, it always equals 3. Because remember, the average rate of change is the slope of the line that connects those 2 points. Well, if my function is a linear function, the graph is always going to be a straight line. It always has a constant slope, which is this number right here, 3. Right? So no accident that this number is the same as these two numbers. Average rate of change is the slope. In this case, it's all 3 for a linear function. And if you have a function in this form, it's going to be a linear function with a constant slope.